In this video, we're going to talk about geometric series. Just like arithmetic series or arithmetic series, you could say it either way. Series is just adding up all the terms or some of the terms in a sequence. So for geometric series, it's adding the terms in a geometric sequence together. For arithmetic series, you can only add up a finite number of terms in the sequence. For geometric series, you could add up a finite number of terms, or for certain examples of geometric series, you could add up infinite terms together, the entire sequence. It depends on what the sequence is, and we're going to talk about that later. Right now, we're just going to focus in on the finite geometric series. So just like with arithmetic series, the sum of a finite geometric series is denoted by the partial sum S sub n. And I'm just going to give you the formula for it, because deriving it would take too long. S sub n is equal to, so that's the partial sum, is equal to the first term times 1 minus r to the nth power, all over 1 minus r. So this is the partial sum of a geometric sequence or series. Summation notation, just like for arithmetic series, it's just another way of saying do this problem. Do this addition. So I have that sigma sign. That means the sum of, take the sum of, going from the smallest n value, so the smallest position term that you have, to the highest, so greatest n value goes on top, and then the explicit formula for a geometric formula for a geometric sequence goes here. What this says, just to recap, this says take the sum of this series from this n position, so this term, to this term. This is the explicit formula that you can use to actually find what the terms are for each one of those positions. Okay. All right, so let's do an example of I'm going to turn this problem, or this example, I'm going to turn it into summation notation. So I have 8 plus 16 plus 32 plus 64 plus ... for the first 10 terms. First thing I want to do is I want to find what is my common ratio. So I know this is a geometric series. I am multiplying by 2 each time. So R, I know my common ratio is 2. The next thing that I need for my explicit formula that I'm going to use in my summation notation is the first term. I know the first term is 8. So what I have here, I'm using the sigma notation. So I'm using the sigma sign that says take the sum of. I'm going from the first term, so this is a sub 1, I'm going to a sub 10, because I'm doing for 10 terms. I'm starting at n is equal to 1, so the first position term, to the 10th position term, so 10 goes on top. My explicit formula for a geometric sequence, I take the first term, which is 8, I multiply by the common ratio and raise it to the n minus 1 power. This is summation notation for this problem. For the next one, first thing I'm going to do is find my common ratio. I know as I go from term to term, I am multiplying by 4 each time. So R is equal to 4. My first term is 3. I know I'm adding for 6 terms. So summation notation, I'm starting with n is equal to 1. This is a sub 1. I'm going to a sub 6. And so I put a 6 on top because I'm doing 6 terms total. And then I have the explicit formula that goes next to it. So I have 3, the first term, times the common ratio, which is 4, raised to the n minus 1 power. Okay, and that's my summation notation for this example. So that's saying add up from the first number to the 6th number in the series. Here's the explicit formula for the series to find the other terms you don't have already listed. And the last one, I want you to try this example on your own. So pause this video and try this example on your own. Okay, what you should have done, you should have found the common ratio first. So as I go from term to term here, to get from 8 to 2, what do I have to multiply by? 1/4. To get from 2 to 1/2, I have to multiply by 1/4. To get from 1/2 to 1/8, I have to multiply by 1/4. This is probably the two numbers that was easiest to find that with. then I know my common ratio is 1/4. I have a sub 1 is equal to 8. Now I'm going to write my summation notation. I have n is equal to 1 on the bottom, 5 terms. So 5 on top. And then I have 8, the first term, times 1/4 raised to the n minus 1 power. Okay. All right, now what I want to do is I want to use the formula for the sum of the geometric series to evaluate the sum of the series. I'm using the same examples as above. So for 8 plus 16 plus 32 plus 64, I already have the important information. I'm going to use my formula for the partial sum. This is a finite number of terms, 10 terms, so is 6 terms, so is 5 terms. So for all of these examples, I've been given a finite number of terms. So I'm going to use this formula that we went over from before. So s sub n is equal to the first term times 1 minus r to the nth power all over 1 minus r. And I'm going to plug in all the information that I have. Well, I have it from above. I'm doing s sub 10. So I have 10 terms. So s sub 10, the sum of the first 10 numbers, I'm starting with 8, that's my first number, times 1 minus r is 2. I'm raising that to the 10th power. And then I'm putting that over 1 minus 2. So the next step is to simplify that and say the sum of the first 10 numbers, the partial sum, is equal to 8 times 1 minus 2 to the 10th power is 1024. And then I have that all over -1. To simplify further, 8 divided by -1 is -8 times, in parentheses, I have 1023. And my final answer is the sum of those first 10 terms is 8,000. Nope, that's not right. 8,184. For the next example, I have my important information up here. I'm plugging that into my formula. I already have the formula written here, so I'm not going to write it again. I'm just going to do s sub, I'm adding the first 6 terms, so s sub 6 is equal to, I have my first term is 3. I'm multiplying that by 1 minus 4 to the 6th power. And I'm dividing by 1 minus 4. When I simplify this, I'm going to get s sub 6 is equal to 3 times 1 minus 4,096. 4 to the 6th power is 4,096. All over -3. You're going to need a calculator for this section, so make sure you have one. I have then simplified 3 divided by -3 is -1 times what's in parentheses is -4,095. And then my final answer, the sum is 4,095, positive. That's the sum. For the next example, I want you to pause the video and try this on your own. All right, what you should have done here, you should have used that formula again. I'm doing s sub 5 is equal to, I have my first term is 8. I'm multiplying that by 1 minus 1/4 to the 5th power. So I should put this in parentheses so I don't get confused. All over 1 minus 1/4. And then I simplify, so don't be scared of the fractions. Whoops. S sub 5 is equal to 8 times 1 minus 1/4 to the 5th power is 1 over 1024. I'm putting that all over 3/4. And then I get S sub 5. I don't know why I keep wanting to write 6. S sub 5 is equal to, I'm going to just take everything I know, or simplify everything. So the first term, I'm going to write it as fractions because I don't want to be multiplying fractions together. So I have 8 over 1 times what's in the top is going to be 1023 over 1024 times, when I divide by a fraction, I can change it to multiplication by flipping this term to its reciprocal. So I have times 4 over 3. And when you do all of that in your calculator, and you could have just changed this to a decimal to begin with, you get approximately 10.656. Probably changing it to a decimal would have been easier. Now we're going to talk about infinite geometric series. I said that sometimes we can find the sum of an infinite geometric series, and we can do that when the series converges, and we're going to talk more about that later. So we're going to talk about how we know if it converges or diverges, and what does that mean. For some infinite geometric series, the partial sum, so s sub 1, s sub 2, s sub 3, s sub 4, if I look at them as like a list, if they form a sequence, I can see it approaches a limiting value. So I'll see the sum is getting closer and closer. The partial sums are getting closer and closer to some number. So it has a limiting value. The limiting value is going to be the sum of the infinite geometric series. Now we're going to do an example to show us what that limiting value means. What does that mean? So to understand the concept of an infinite sum of a geometric series, I want you to follow these steps. Step 1, I want you to get a piece of square paper. So take a regular piece of paper and make it into a square. And then you're going to let that square represent one whole unit. So pause the video if you need to, get that paper out. That's going to represent one whole unit, that square. You're going to cut the paper in half, and you're going to place one piece of paper on your desk and keep the other piece of paper in your hand. The paper on your desk is going to represent the first partial sum of the series, and I know it's 1/2 of the whole I started with. So do that now. And then step 3, you're going to cut the paper in your hand in half again, adding one of the pieces to the paper on your desk and keeping the other piece in your hand. The paper on your desk is going to represent the second partial sum after you do it a second time. And you're going to keep repeating this process as many times as you are able, and then record the first 6 partial sums. So really you just have to do this 6 times. The first one, once you put the 1/2 down, the paper in front of you should look like this, right? A rectangle, half of a square. After you cut the half in half, that's in your hand, you should end up with, now you're adding to your pile on your desk 1/4 to that 1/2. So my second partial sum is 1/2 plus 1/4, which is going to give me 3/4. The next thing you're going to do is cut the 1/4 that's left in your hand, cut it in half. After you cut it in half, you're placing 1/2 on your desk in front of you. This piece of paper is 1/8, and I should make this larger. This piece of paper is 1/8. And then you're adding 1/8, so 1/2, 1/4, 1/8 together, and you're going to get a total of 7/8. Then you're doing it again, you're cutting it in half, you're going to add half of that. Again, this is 1/16. I'm not going to keep drawing on the diagram, but you'll have 1/4, 1/8 plus 1/16, and that will give you a total of 15/16. And then we can see a pattern from here. You can continue breaking it down on your desk, but I'll have 1/4, 1/8, 1/16 plus 1/2 plus 1/32. I'm cutting the denominator, or I'm multiplying the denominator by 2 each time. I'm really dividing the thing by 2 that I add, and I'll have 31/32. And then for the last one, I'll have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, which will give me a total of 63/64. As I continue the process of placing half of the remaining paper on my desk, what happens to the amount of paper on your desk? It's getting closer and closer to what? The amount of paper is getting closer and closer to 1. So the amount, 1 whole unit, it's getting closer and closer to that 1 square. The amount of paper gets closer to 1. The amount represented by the original square. Okay, it's getting closer and closer to the original square, which makes sense, right? In this example, well, actually, we'll talk about that later. For this example, the first 6 partial sums are plotted here. So they're plotted here. I can see, or can I see, do these partial sums appear to be approaching a limiting value? So this is the partial sum, and this is the, or I'm sorry, whoops, JK. This is the n, and this is the partial sum. Does it appear to be approaching a limiting value? Yes, as I continue increasing the amount of times I'm adding numbers together, I'm getting closer and closer to 1. So yes, it does, and that number is 1. Now we're going to consider the geometric series 3 minus 1 plus 1/3 minus 1/9, etc. I want to list the first 7 partial sums. I'm just going to give them to you for time purposes. So I'm going to say the first sum, so just adding the first number by itself, is 3. The second partial sum is 3 minus 1, which is 2. The third is 2.33 about, if I add the first 3 terms together. The fourth partial sum is about 2.22. If I add the first 5 numbers together, I get about 2.259. If I add the first 6 together, I get about 2.247. And if I add the first 7 together, I get about 2.251. Does there appear to be a limiting value here? Well, as I increase in the partial sum, I'm getting, if I look at this list together, I'm getting closer and closer each time to some number, and it looks like, so yes, and it looks like that number is probably 2.25. So the sum is the same as the limiting value, 2.25. The next thing I want to consider is the geometric series 2 plus 4 plus 8 plus 16 plus 32 plus blah, 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 blah. I'm going to list the first 5 partial sums here as well. So the first one is 2. The second one is 6. The third partial sum is 14. If I add the first 4 numbers together, I get 30. And if I add the first 5 numbers together, I get 62. Does there appear to be a limiting value here? Am I getting closer and closer to some number? No, not a finite number. I'm going to infinity. So does there appear to be a sum of the series? No. The sum gets larger and larger. There is no limiting value. There's no limiting value here. The thing that's going to tell me if the series converges or diverges is what the R is. So if the R is less than 1, let's look at the examples, or let's look at what our R was for all of these examples. So R here was 2. R here was negative 1/3. R here, in this case, was 1/2. So for 1/2 and 1/3 and negative 1/3, so when the absolute value of R was less than 1, the series converges. I know it converges. The sum gets closer and closer to a single value. The sum gets closer and closer to some value. Some like that, not some like that. Then for the one example that I had where R was greater than 1, the absolute value of R was greater than or equal to 1, the series diverged. So the series diverges. And that means the series has no limiting value. So I'm going to look at 2 examples of a converge example and a diverge example. Converge example, I would see the numbers decreasing each time. I would have maybe R is equal to 1/2. So then I know that the absolute value of R is less than 1. So if I had R is equal to 1/2, an example would be if I started with 100, the next term would be 50. The next term I add would be 25. I would have 12.5 plus ... That would be a converge example. For a diverge example, I might have R is equal to 2. That way, the absolute value of R was greater than 1, or greater than or equal to 1. So an example is if I start with 2, I'd add 4 next, and then 8, and then so on. So that would be a diverge example. I'm not going to graph those right now to save time. To recap, if the series converges, that is the only time that you can find the sum of that infinite geometric series. And there is a formula for it. So if it converges, you can find the sum. That's the only time. And here is the formula. S sub n, the sum of the geometric series, is equal to a sub 1 just a sub 1 over 1 minus r. It's similar to the partial sum of a finite geometric series, except 1 minus r to the nth power is becoming 1. It gets closer and closer to 1 because r to the nth power gets closer and closer to 0. So I'd have 1 minus 0, which would be just 1. I want to use this formula now. So this is the formula. I want to use this formula if the series converges. Otherwise, I can't find the sum. So I'm going to see if it works for this example. The first one here, 2 over 3 to 4 over 9. I'm multiplying by 2 over 3. Here, I'm multiplying by 2 over 3. This is it converges. I know it converges because r is equal to 2/3. And then I can use this formula. So I'm going to use it. I know S sub n is equal to a sub 1 over 1 minus r. I'm plugging in... So sorry, you don't write S sub n, you just write the sum, because it's not S sub n anymore. We don't have an n. It's just the sum is equal to this. So the sum of the entire series is, I'm doing a sub 1, which is 2 over 3, all over 1 minus 2 over 3, which gives me 2 over 3 over 1 over 3, which is the same as 2 over 3 times 3 over 1. Dividing by a fraction is the same as multiplying by the reciprocal. And when I cancel out my 3's, I get the sum is 2 when I add it together. For the next example, 2 to 6 to 18, I can see these numbers are increasing each time. I'm not getting smaller and smaller each time. I'm getting bigger and bigger. So this is a diverges, but I can also tell because as I go from term to term, I'm multiplying by 3. So r is equal to 3. So it's because r is equal to 3, which is greater than or equal to 1. I don't need to find the sum there. For the last example, I know as I go from term to term, I'm multiplying by 1/2. I'm multiplying by 1/2. So I know this is it converges because r is equal to 1/2, which is less than 1. And then I use my sum formula. So I'm doing 1 over 1 minus 1/2, which is equal to 1 over 1/2, which is 1 times 2, which is 2.